Greetings and welcome to my new calculus channel. So in the previous 2 or 3 videos I talked about tangents, and I'm now going to show you that the ancient geometer Apollonius of Perga defined the tangent with respect to the conics. Okay, in other words, he defined the main property of a tangent line. Since it was already previously defined in Euclid's conics, which were lost somewhere along the line. Okay, so why is this important? It's important because it shows us that the idiots of mainstream academia, who believe that tangent lines can cross curves, have gotten it all wrong. And I'm not going to deal anymore with those idiots, but I'm going to go straight to the work of Apollonius. So in Proposition 11, where he deals specifically with tangents. Now, of course, tangents are referred to before this point, but before this point here, they're referred to with respect to the definition, to the original definition of Euclid. But in this proposition, a main property of a tangent line is proved for all the conics. Well, first of all, for the parabola, and then for the rest of the conics, the hyperbola, the circle, and the ellipse. All right? So it's proved in 2 parts, in part 1 and 2, which I'll show you in a moment. Right. So let's see how this is proved. Now, if we go to this article, which I shall place a link to on academia.edu, it's interesting to understand that the idiot Gottfried Leibniz decided that a tangent cuts a curve in 2 points, infinitely close, which is just absolute drivel, and try to redefine this important concept of the tangent line in terms of the bullshit of mainstream mathematics academia, which is, the understanding that every number corresponds to a line, to a point on a number line. So we're going to see now how to understand this in terms of the way Apollonius understood it and proved it. So propositions 1 to 3 of Archimedes' quadrature of the parabola, these very important propositions here, were never proved by anyone. Okay, no one in the history, and they're not recorded anywhere. Well, actually they are. I've actually proved these things, but I'm not going to be sharing them with you for a very good reason. And I might change my opinion, my stance on that if I'm recognized as the greatest mathematician today and rewarded accordingly. But anyway, that's a different topic. So these 3 propositions in the works of Archimedes deal with chords parallel to a tangent line. So if, for example, you have this particular chord here, Q and Q dash, and it's parallel to the tangent line. What it means is that if you draw a parallel to the axis or the diameter of the parabola, it will intersect this chord. Okay, that's what it means. That's the first proposition, unproved. Okay, and the second is that if you extend, let's say, a tangent line at Q, as you see over here, down here, at Q to T, then the distance PT and PV are equal. And the final one states a very important property of the parabola, that is that the y ordinate is equal to the square of the abscissa. Okay, and that's how you see it in modern mathematics. So now, as I mentioned, Apollonius defines tangent line and proves that a tangent line never crosses a curve at the point of tangency. So somebody might say, well, he didn't really define it, but he did, because he defined it in terms of its main property, that it never crosses at the point of tangency. So while he used the most primitive definition in the lost conics of Euclid, he still defined it in terms of its main property. Okay, And that's what I say over here. So a tangent line never crosses a conic at the point of tangency. And by the way, it applies to all curves, not only conics, as the mainstream baboons think. Why? And I'll explain to you in a moment. So if you look over here, this, suppose you have a curve like this. Okay, something like this. Okay, it still applies here too. And how's that? Even though there is no diameter or axis for the entire curve, but you can break the curve up into parts. Okay, in which case you can have chords and some relationship between a diameter, and the same can be said for the rest of the sections. So it applies to any curve, not just the conics, as those incredibly stupid and ignorant fools called mathematics lecturers and teachers tell you. Okay, so I'll get back to that in a moment. Now, we see several of these mentioned also in the Latin translation, and here's one where it talks about this same proposition. Okay, in Latin, there are no original Greek texts except those that were found. I think the first 3 or 4 books. I'm not quite sure. And so let me give you a brief introduction. In this graphic that follows, you'll see the first part for the proof of the parabola. So if we look at this proof here, as written out by Sir Thomas Heath in his translation, what he does is assumes that let's go to the main diagram here. It's much easier. What he does is assumes that the tangent line KP falls inside, as you see over here in this diagram, okay, in this diagram here, that it falls inside. So in other words, it doesn't go like that, but it falls inside, right? Then he says, if that's the case, then PK will be bisected by PM, right? PM is the diameter or the axis. It'll be bisected. But if that's the case, the only way we can understand it being bisected is if we extend it, because nowhere over here is it bisected. It's a simple proof, but it's ingenious, because if it is a tangent line and it meets PM, then it has to be bisected. But if that's the case, it falls outside of the parabola on this side here, you see, which it doesn't. And so it means therefore that KP must touch it at P, and it falls outside of the parabola. All right. So that's the first part. The second part is quite interesting because Apollonius makes the constructions that you see here, okay, over here, with QV and Q dash and V dash as being parallel chords. And then what does Apollonius do? He says in his proof here, that KV squared, the ratio of KV squared to PV squared is greater than well, actually, this is Heath's mistranslation. It doesn't say the ratio is greater. It says the measure of the ratio of this ratio is greater than the measure of this ratio. Remember that in geometry, no ratios are greater than other ratios, okay? You cannot, for example, have a ratio that is greater. So, for example, if P to Q, if P compared with Q is greater than or is equal to the ratio R is S, it can only be equal. It can't be greater or less. It's only equal if P is equal to R and Q is equal to S. Now remember, P, R, Q, and S are not numbers. They're magnitudes, such as line segments. Okay, so they can't be greater than or less than, but their measures can. You morons. Okay, so Heath did not know this. That's why he went ahead and wrote it like that. So personally, I would have wrote it as the measure of these ratios. But now, how did he get this expression here? It's pretty interesting, isn't it? He writes that KV, or rather that KV squared, the measure of KV squared to PV squared, is greater than QV squared to PV squared. How does he get to that conclusion? Well, let's look at the diagram. Here's the diagram, okay? So since KV is greater than QV, its square must also be greater than the square of QV, right? And therefore, the measure of that with PV squared must be greater than the measure of that of QV squared. Okay, so that's this first step here. This first step. Then he does a little jump here where he says PL times PV, the measure of PL times PV, will therefore also be less than this part here. Okay, PL times PV will also be less than the measure of this ratio. How is that possible? Well, if you extend this diagram here, so let's go back to paint. So if you could say take QV, the length of QV, and if you extend it, it will meet in L, right? He doesn't even mention L because it's within context, that's what he means. And then, of course, if this becomes Q here, and then QL squared must be greater than QP times PL, okay? QP times PL must be greater than. So that's the part that he mentions in here when he does this. And finally, he ends the proof with a relationship that is shown in Archimedes's first three propositions. Short, brilliant, irrefutable proof that a tangent line never crosses at the point of tangency. But what do the morons at Wikipedia say? That they know better. You know, the ancient Greeks were almost like gods. They were way, way, way more advanced than anyone before or after them. I mean, don't even look at the modern Greeks or their descendants. Most of the modern Greeks are a bunch of dimwits. How did it happen? Well, they were dominated, ruled over by other nations. They were degraded in their DNA. They simply are not anything like the ancient Greeks. I mean, sharing some DNA with the ancient Greeks doesn't mean anything. Okay, so I hope I've given you a good introduction here, and I'll place a link to this article with the video, and also I'm going to, believe it or not, place a link in the article and upload it to academia.edu. If you're not already a subscriber, become one. My name is John Gabriel, and this is a new calculus channel. Till next time, goodbye.